So from now, people can attend, and
Mm-hmm.
you can hear what we say, and what they can see what we show. Okay. So. Hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal pump from scratch in CFturbo, and then how to simulate it and evaluate it in TCFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. I hope all the techniques works well. And anyway, in case of any technical problems, feel free to contact us in the future and we will gladly answer all your questions and comments. I will start with the webinar speakers. So I will introduce us a little bit. So this is me. My name is Luboš Pirkl. I am co-founder of CFD Support. My current position at CFD Support is telling the world what we do. And I'm gonna guide you through this through today's webinar. Here in our Prague office, I'm sitting with my colleague Radek Máca. Hello, Radek.
Hello, Luboš. Hello, and hello to everybody who is watching us.
So, Radek, are you ready for the webinar?
Yes, I am ready. for the webinar, so please go ahead.
Okay. And together with us on the other line, there is Oliver Felde from CFturbo in Dresden. Hello, Oliver.
Hello, Lubos. How are you?
Yeah, I'm fine. So the same question. Are you ready for the webinar?
Yes, I am. And I'm looking forward to have this webinar with you again.
Okay, I only note that Oliver is Senior Manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms into CFturbo software. And I'll go, I'm sorry, here is Oliver. And I'll go a little bit back to Radek. I forgot to mention Radek is our head engineer and senior developer of of TCFD. So this is us. We will guide you through the webinar. About the webinar program, the webinar is going to take about 1 hour. There will be 4 parts in this webinar. The first part is this general introduction. In the second part, we can call it the design part or CFturbo part. There will be a live example where Oliver is going to introduce CFturbo a little bit. And then he will show us a live example of centrifugal pump design from scratch in CFturbo with the final export of the designed model to TCFD. In the next part of this webinar, we can call it a simulation part or TCFD part. There will be another live example where Radek is going to show us the TCFD simulation of that centrifugal pump, which was exported by Oliver from CFturbo in the previous section. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions. There is a special window where you can put your questions. All the questions will be answered. Some of them will be answered right in this webinar. The rest will be answered via email later after we finish the webinar. So Q&A is quite important part. So feel free to put your questions. It's your time. Just get involved. Take the opportunity and put your questions, and we're here to answer them. Okay, so I think we can start with the CFturbo part. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Okay, CFturbo is a German company that is based in Dresden and Munich in Germany, but we also have a daughter in the United States, which is CFturbo Incorporated. Our main product is the design software CFturbo, which is a modern, powerful, and user-friendly software tool meant for the conceptual turbomachinery design. Right now, we have something like 200 active clients globally. And CFturbo contains different modules for the design of, for instance, pumps, both axial as well as radial, fans and blowers, compressors and turbines. And again, those can be both axial and radial. And if you want to design a complete stage of a pump, for instance, you might need stators. They can have vanes or they can be vaneless. And also, of course, for radial machine, it's important to have a volute, and that's why there's also a volute module. Right now, with our software, we serve the industries given here. Amongst them are the aerospace industry, automotive, consumer products, energy, oil, and so on, and also the semiconductor industry, because in almost all desktop computers, for instance, there are fans, and those have to be quiet and efficient, and that's why CFturbo can be used to design those turbo machinery.
Okay, so you are the presenter now, Oliver.
Okay. You should be able to see now the GUI of CFturbo.
Yes, we can see it. Please go ahead.
Okay, so what I want to do is in that little demo, I want to design a centrifugal pump from scratch. And to this end, I choose from the machines one can design with CFturbo the pump machine. And in here, the starting point is to define a design point, because what we do in CFturbo is we do a best point design on the basis of that operation point, which is the one that the machine is run in most of the time, and that's why it should be a best efficient design in this design point. So the global setup for the pump consists of a flow rate, a head, a speed, and what we also need is some sort of fluid information, because if we don't have the density, we cannot calculate, for instance, power or pressure differences and so on. In general, if there is something typed in CFturbo, on the right-hand side, there are always as much information as possible displayed. So here, for instance, we get from the design point the specific speed, and with the help of the specific speed, one can tell what is the best meridional contour for that type of machine, or what might be the best diameter of the impeller, and so on. So that's why there is that yellow panel on the right-hand side. Once this has been defined, the global setup, CFturbo asks what component of the stage should be the next to be designed. I'm going to start with the impeller because that's the central component of the stage. And here I have to run through a couple of design steps which contain some parameters and which initially also have suggestions made by CFturbo for geometric parameters like impeller diameters. So here, for instance, on the parameters page, there is, just for an example, a work coefficient given, which is 0.82. And just to give you an idea where those numbers come from, I'm going to click on that little icon, and I'm guided through what we call approximation functions. And in here, there are a lot of empirical functions and correlations implemented, which will give the user a hint what is a good parameter and which parameter one should choose in order to get, for instance, a good efficiency. So this work coefficient clearly comes from the coordinate diagram, and the argument is just a specific speed. All those empirical data are just taken from either personal investigations here at CFturbo or from publicly available literature, but they can be always overwritten by the user just in case there might be some in-house knowledge which is better suitable to the kind of application that is from interest in the company. And when this personal knowledge is implemented or typed in here, it's going to be saved in a file which is stored in the company, and it still will remain with the company, and it's not going to be published. Anyway, these kind of parameters are used together with the solution of some balance equations like Euler equation or continuity equation, in case one either presses a calculate button like this, or in case one is in the automatic mode. If this is the case, I quickly want to show what's going to happen if I change a parameter. Then initially this set of equations is solved again for the newly changed parameters, and you see here, for instance, the consequences for the specific speed diameter. Or if I go to the meridional preview, then you see which impact this change of the work coefficient would have of the design. Okay, but I don't want to stay in the automatic mode, and I also want to get rid of that decimal places. So I just change numbers and make them somehow round. Once that is finished, the next design step is the meridional contour design. So here the meridional contour is represented by Bézier curves with the appropriate control points. One can grab and drag and drop them, and on the right hand side again there are a couple of informational things that can be displayed. So for instance, the curvature or the static moment. And what we also have is some sort of very basic CFD. So here, for instance, we have the solution of the potential flow within this meridional contour. And this solution is done after any change of any contour points, for instance. Once I'm happy with that initial design, I press OK, and I see something in our 3D viewer. The next design step is to define blade angles at leading and trailing edge. Again, Euler equation is used together with some formulas or rules for the incidence at the leading edge or the deviation at the trailing edge. So here, for instance, 3 different models are implemented. And if I again automatically calculate the blade angles, I'm going to end up with those given here. Again, I don't want to stay in the automatic mode, and that's why I uncheck this checkbox and go to the next design step, which we call the mean line design step. In here, the blade, the 3D geometry of the blade, now having a 0 thickness, is represented by MT Bézier curves. The MT Bézier curves have the big advantage that at every point one can measure the tangential angle, and this angle is exactly the blade angle. And using Bézier curves with boundary conditions like those here, given a tangential direction, one can make sure that the trailing and leading edge blade angles that have been defined in the design step before will remain the same no matter what I do here. I can grab any of these Bézier points, but the blade angles at leading and trailing edge will stay the same. And that again means that the incidence will stay the same, as well as the relative flow at the trailing edge. Okay, I can again directly type in geometric parameters like an average wrap angle, and to this end I'm typing in 75 degrees. And again, there might be, or there is some change in the 3D view, and the change is given here: blades with 0 thickness. And to apply some thickness, the next design step, which we call blade profiles, is chosen. Here one can either use a simple design mode where one has a linear interpolated thickness distribution between control points, or one can go to freeform and can have again Bézier curves to represent this thickness distribution. I'm going to stick with the simple approach, and after pressing OK, I have blades with a certain thickness. but still the edges are very sharp, and especially at the leading edge, I don't want to have this. And that's why I'm choosing a elliptic leading edge with a certain half axis ratio of 3 or 2 or so. And very often with centrifugal pumps, the trailing edge is trimmed at the outlet, and that's why this is the option I go for. Okay, once that is finished, I'm ready with a design, with the first design of the impeller, and I'm going to save that. So maybe I have a test directory, and I just call it pump1. Yeah, because I want to have a nice spinner here, I'm going to go back to the main dimension and set the hop diameter to 0. And whilst doing that, you can see clearly that everything in CFturbo is parameterized, so you can change any geometric parameter at any time, and you will get immediately a 3D update. The spinner again is designed by introducing some extra curves on the hub. So like this, and another curve like this. Again, a right click on the control point gives me the opportunity to type in certain values that I would like to see here. So for instance, the Z coordinate should be 40 and radius, for instance, 60 millimeters. And to get a nice spinner, of course, I don't want to have a straight line here, but a Bezier curve. And also what I want to do is, I want to have a tangential transition from one part of the curve to another. And yeah, that's fine for the time being. And if I press OK, I can see clearly what I got from that. And this is a nice impeller with a nice spinner in the center. Okay, so that was the impeller. One thing which is not necessary for the geometric design, but later on for the CFD simulation, is I'm forcing a CFD setup, which means a segment is generated, and optionally one can also activate an extension for this data, rotor stator interface. But I'm going to add a volute at the outlet of my impeller. To this end, I just go on the interface, add a volute, type in, or either accept the initial suggestions by CFturbo or type in data that might come from your restrictions or something like that. So for instance, I'm going to do that a bit smaller here. And then the next step is to tell what is the general shape of the volute. So it can be quite different. So there might be a rectangular shape, a trapezoidal. It can be asymmetric, line segment, stuff like that. And it can also be symmetric or unsymmetric. So I could have, for instance, a rectangular shape on the right-hand side and a round one on the left-hand side. And it even can change with the rep angle. So here it's from rep angle 0 to 360. It's just the same shape. But if I would add another section here, and then I could say, okay, I want to have from 0 to 180, it should be symmetric, for instance. Whereas here it should be not, and it should, well, for instance, the Bezier type, something like that. Yeah, but I want to keep it simple. make it symmetric again, press OK. Nothing has happened so far because I just had the interface defined as well as the general shape. The spiral itself is now defined by that third design step, and here I can either use some rules, very famous rules established by Flyder some, I don't know, 50 years ago, or the Stepanov rule. One can also use just a geometry-based approach, and to this end, one can define a final outer radius or an area, or even a area to radius ratio. So if I go for the radius, for instance, I again can override the suggested value, and I can also tell what should be the progression of the radius with respect to the rep angle. So this would be, for instance, a linear one, but I can have it in a way that it might rise early at small rep angles and then go over into a linear part like this. Again, a lot of information on the right-hand side. Very interesting is, for instance, the area radius ratio. Quite often, this should be linear according to the very basic design theories. Once this is ready, I'm going to see also something in 3D, because now we have a spiral. What is missing now is the inlet diffuser and the cutwater. And this is quickly done in the last two design steps. So I can tell him, for instance, what is the diameter of the outlet diameter of the diffuser and what is the length. So quite easy. I can change the direction of the diffuser, and I even can have a Z band if I like, but this is nothing I'm going to show in that webinar. And when I'm happy with that, I can directly jump to the very last Volute design step, and that's the cutwater design. And here I'm going to choose a fillet cutwater with a diameter of 3 millimeter, a radius of 3 millimeter. And if I press OK, then the volute will be displayed also in the 3D view. In order to make a nice design which can be run in CFD, I want to quickly add an inlet pipe, which should be an axial diffuser with a certain length. So for instance, like that. That's quickly done, and again, the result can be seen here. And now, just because I want to prepare everything for the CFD, I know that I have to rename the components in order to avoid some characters that for instance, TCFD don't like to see. So just quickly give them some new names. Okay, and run a CFD setup also for the volute in order to close that gap here. And the final step is to finish the 3D generation of the impeller. And here I have the opportunity to tell him whether there should be some fillet radius at hub and shroud. And that's what I want to do. Okay, and now Oh, that's, now I have, maybe that's a bit too high, the radius. Okay. Now I can go to our export panel where one has access to a lot of CFD interfaces, but also to CAD interfaces. And one has also the opportunity to export the geometry as IGESTEP, STL, or BREP. What I want to do is a TCFD export, and I want to do that for all components. There are some parameters I can choose from, so I don't want to do it fine, just in order to save some time. So I press course. I want to export the full geometry. I could also export just the periodic segment. And if I'm ready for that, I just can press export. And as you see here, there is a TCFD file exported, which is the control file and holds all the CFD boundary conditions and things like that. And there are a lot of STL data with certain names exported, and those afterwards can be used by TCFD in order to set up the CFD run. There's a last thing I want to show you quickly before I hand the presentation over to Radek. What we have done so far is the design of all the solids and surfaces that cover the fluid room, but what can also add wall thicknesses, for instance, to hub and shroud, in order to do a design of the what we call the material domain. So for instance, here I can just add a wall thickness to the pipe. So that would be one thing. And I can do the same with the impeller. And to this end, again, I go to hub shroud solid and say, I want to have a solid at the hub and at the shroud. And very quickly, I want to show you how I can manipulate this. So for instance, I can have some sort of a hole here in order to get space for a shaft. And I can insert Bezier points, and they can be done like that. I can split these lines, and can move that split point, can switch back to a line segment once I had a Bezier curve, and also I can remove that. Yeah, and if I finish that and make a model finishing again, I will have in our 3D model not only the flow domain. Let me uncheck pipe and volute. So this is the flow domain, but what we also have is the material domain, and this is the one that I just designed together with the thickness at the shroud and some contour at the hub. Okay, and this is what I wanted to say for the time being, and now I would like to make Radek the representer.
Okay, thank you, Oliver, for the turbo machinery design part. I will switch the presentation back to me. And yeah, so the pump is designed now. It was perfect. Thank you, Oliver. It looks very easy to do that in the right hands and right software. And now we switch to turbo machinery CFD part of the webinar. So yeah, so before I do that, please let me give a brief description. What is TCFD? So TCFD is a unique software developed by Czech company CFD Support. It's a smart, easy to use and affordable CFD software. TCFD was designed for CFD simulations of all standard rotating machinery, such as fans, pumps, compressors, turbines, hydro turbines, both radial and axial machines, both compressible and incompressible fluid flows. The numerical solver of TCFD is OpenFOAM. And what's important, we at CFD Support, we believe that TCFD is unique, at least for reasons. So number one would be TCFD is always perpetual, which means our clients can keep the machine CFD forever and they can use it for unlimited number of users, jobs, or cores. What is paid for is in fact the first delivery of this software and later technical support and maintenance. This gives the investment in TCFD a permanent value, and also for this means that our clients can scale their CFD simulations in a really big way. Number two would be TCFD is fully automated, which means all the workflow from the initial data to the final results, it can be run by a single click or a single command. And all the process is being done automatically. And for this reason, TCFD is extremely effective. Number three would be we deliver very good technical support, which we are proud of. We keep custom approach to every customer, to every issue. We never leave behind any of our clients' requests, and we are very flexible in it. And we support our clients even in matters out of turbo machinery field, for example, in numerical mathematics, physics, CFD, or even software engineering. And finally, the real tutorials are included in TCFD, so the TCFD user has no doubts about the best practice settings. There are real machines included that are already preset. User can basically take one of those tutorials, replace the geometry with his own geometry, just modify the settings and run the simulation. The rest of the workflow is automated anyway, and so this means that the requirements on the user skills are pretty low. So these are the uniquenesses of TCFD. There are many other benefits of using TCFD. I'm not gonna go for all of them. I only finish with my last point here, that TCFD is developed in a way to support the added value activities of its users. And the beauty of TCFD is that it's the user who decides how deep to dive into CFD, or even not to dive at all. It's the decision of the user how deep to go, and also all the options remain open. So it's proper CFD tool as well as automated tool, automated code. Okay, so this is just a brief introduction, and I think now it's time to hand over the presentation to Radek. So Radek, are you ready for your part?
Yes, hi Luboš. Yeah, I am ready for my part. So please, can you give me the presentation, or should I?
Okay, and I'm doing it right now. Okay.
Okay, so I hope you see my screen. Yes, yes, you see. So hello again, and because Luboš has already said all important information about TCFD, so I can jump directly into the practical part. So I will start with the data which Oliver has generated a few minutes ago. So I will use my favorite file browser. Here's my working directory. Here I have this CFD-Turbo export webinar, and this is what we get directly from CFturbo. So there are two things to start with TCFD. So first part of the input is the configuration file, which is automatically generated from CFturbo, and it basically contains all necessary parameters which defines the CFD simulation. And the second part of the input is the geometry. So what is nice that from CFturbo we get smooth geometry which can be directly used for meshing and which can be directly used for the CFD simulation, because we have the geometry of the fluid domain. So I can, for example, click automatically at one of these files just to visualize that. So as a part of TCFD, there is a paraview viewer, so we can nicely follow the geometry. For example, this is the hub. We can, for example, show the pressure side of the blade. Yes, and in this, and the fluid domain for each component is divided into the sensible part, which defines each part of the blade and of the domain. And this is the best input you can get for CFD setup, and especially for TCFD. So now I can directly run the TCFD software. I have two options. I can run the icon at my desktop, or I can directly run this configuration file because it is automatically associated with TCFD. So this is the graphical user interface for TCFD. It has been implemented directly into the paraview, and paraview is a toolkit which can be used for CFD data or general data visualization. It is very powerful tool, and with connection with TCFD, it can be now used both for CFD simulation, for CFD setup, and also for post-processing. So the graphical user interface of TCFD is here. So what we can see here is the pipeline browser. So there are special filters which can be layered one each another, and any filter which is standardly provided with paraview and with, for example, with our own filters can be applied, and this brings an unlimited variability of the post-processing of the CFD simulation. Okay, but we need to start from very beginning. So here in the left menu, this is the TCFD setup. So I will quickly go through all of these menus and briefly introduce what can be set up in there. So here in general, here we load the configuration file, or if we are starting from scratch, we define the TCFD file in which our setup will be stored. Then there is new feature, because I am working with the newest version. So we have developed this check setup, which makes the setup easier for the user, because anytime during the setup process, we can click it and we get the message if everything is correct or if there are some inconsistencies in the setup. So for example, I will jump a little bit. For example, in the physics, because we would like to simulate a pump, so the fluid name is water, and I can check, for example, the compressible, that I would like to enable compressible mode, which doesn't make a sense for water, and I click the check setup, so I can immediately get the message that something is wrong, and it tells me that pump flow must always be incompressible, which surely has to be. So I need to uncheck it, and now again everything is correct. So this is the check setup. The machine time, of course, is preset for pump by CFturbo, of course, but if you're starting from scratch for another type of machine, of turbo machinery, you can choose between these. The new we have added within this newest version is the propeller for simulation, the open propeller, which can be, for example, wind turbine or propeller of a ship, for example, and the general stator for simulating just the stator parts, pipes, manifolds, etc. Okay, so I will go for the next menu, which is the simulation. So here I can manage the time management. So for today's case, we would like to compute the steady state solution of our geometry. I can set number of processor because my computer, now I'm working at my at my laptop, so I have only 4 cores available. In general, you can use as many cores as you want, so there is no limitation. We have some scalability studies, so we can provide you, and the scalability is very nice. So it reaches more than 90% for over than 100 of cores. Numerical order, sensible choice for incompressible cases is always second. I can enable convergence check, which can stop the simulation before the maximum iteration is reached if the convergence is found before the maximum iteration are reached. And here's some convergence, so it's not so important right now. In the physics, the properties of the fluid, what you can enable is the cavitation risk, which gives you some information about the possible cavitation, which is a tool which works as the post-processing, or it is processed during the simulation, but it just takes the pressure values and evaluate some post-processing using the reference pressure, reference temperature, and so on. But in case of if you enable the transient simulation, so then you have an option to enable the multi-phase cavitation, which is the full multi-phase solver. So now we have cavitation model, just the one implemented, the Schneer-Sauer, with these parameters, and this is the full cavitation model. But of course, because it's transient simulation, it takes much more time. It's much more time consuming and needs to be run on some cluster to get the result very quickly. But the possibility is here. But for today's webinar, I will stay at the steady state simulation. And I will, let's say, enable the cavitation risk. Inside the components, here we basically define the computational domain. So in case there are several options how to import or how to create a computational mesh. In today's webinar, we will create it from the STL files, and the mesh will be generated automatically using the SnappyX mesh tool, which is a standard meshing tool for OpenFOAM. But you can import an external mesh, usually in the Fluent MSH format, so any mesh can be imported directly. So if you prefer your own mesher, you can use it and import just the final computational mesh. And then here in this menu, for each component, you just set the types of the wall, so general inlet for physical inlets, some outlet interface to connecting the neighbors STLs or neighbors parts of neighboring components. For the communication between two components, there are two approaches, main two approaches, so-called mixing plane approach, using some averaging technique. So here, using this value, you define how many strips or how many rings will be used for averaging. Or if you set 0, there is a standard arbitrary mesh interface is called, but in general, for example, in CFX, it is called frozen rotor type. And I think if you enable this mixing plane approach, it is usually called the stage, I think, in CFX. And this is done basically for each component. Because the SnappyX mesh starts the meshing from some simple background mesh, which is built from hexahedras. The definition is here. What is new feature? You can visualize this background mesh to see the finest of your basic mesh. And basically, what is done here, that you set the levels of refinement at each part of the geometry. So basically, this means that, for example, at the outflow, which is this component, this part of this component, there will be level 1. It means there will be cells which are two times finer than the background mesh. But maybe I'm going too much details. What we also provide is the cylindrical background mesh, which is somehow also useful to mesh, for example, pipes and other stuff. But in this case, we use this background mesh. And what is also nice to see is this topology graph, which shows you the connection between each component and how are connected. And this is really nice when you start from the scratch to see if each component is connected to another component and what are the outlets and what are the inlets. All right, so this is the components part. Next one is the speed line. So here you basically define the regime of the simulation of your machine. So now we have this rotation speed, which you can define in radians per second or in RPM. I think it corresponds to 1770. So this is the equivalent definition. You can define more speed lines. So I think pumps always runs at one condition, but for example, for compressors, you can define more speed lines, and each speed line basically holds one speed of rotation. And for one rotational speed, you can generate a map, which, because usually you know your design point, so it should be the best efficiency point, but to really validate and analyze the properties of your design, you should always generate a map which tells you at which condition you reach the best efficiency. So for example, I can define, let's say, 5 points, and this is the maximum number of iteration for the simulation. Okay, so I will keep it for 500 for now. At the inlet condition, so I think we get, because from CFturbo we get the best efficiency point, and if I would like to simulate a map, so just several points along or around this value, I can basically explicitly define the flow rate, or there is a new approach which is denoted as +%. So you can, for example, tell that I would like to simulate the condition which is lower by -10% of my reference value. So the reference value is the one which is not defined as +% sign. And for example, in this setup, I can define the map around my design point. Okay, so in this case, I will generate 5 points, 5 computational points. The outlet condition, because we are simulating the incompressible case, so the reference pressure is 0 at the outlet. It's called kinematic pressure. Initial conditions, so some reasonable guess for the initial condition. Some simulation controls contains some advanced parameter for the solver, like under relaxation factor or some bounding limits for each variable. Here in the SnappyHex mesh menu, you can define some advanced parameters of the SnappyHex mesh measure. So for those who are familiar with it, they can play around with these parameters, and inside the scripting, you can define your scripts which can let's say set some additional tools within the TCFD simulation. And I see that I missed the post-processing part, quite important. So here we define the averaging window. So because we are looking really for the steady state solution, so we can average the solution over the last amount of iteration, in this case 100. At the end of the simulation, the report is automatically generated, and you can here set your favorite units for the pressure, for the mass flow rate, volumetric flow rate, etc. You can define the efficiency probe, so from which parts of the geometry you would like to evaluate pressure drops, the efficiency, which parts of the geometry will be used for torque evaluation and other stuff. You can define the blade-to-blade view, which is a nice visualization commonly applied within turbo machinery to see the values at some radial coordinate at your wheel. So you define the rotating part, which part is rotating. Here, for example, is the 2, because 2 is the rotor part, what is the hub, what is the shrub, because there must be defined for such an evaluation, and which field to evaluate. For example, relative velocity with a LIC, a streamline filter, and at which relative coordinate between hub and shrub you would like to make a slice. For example, meridian average, you can define the meridian average as a post-processing and additional data, for example, for previous simulation. Okay, so now it brings me to the next part, which is the TCFD manager. So after everything is set, I can apply this TCFD manager, and inside the TCFD manager, I can manage the simulation. I can run the simulation. So first of all, I need to click on the write case. I can define my directory name, and after that, I can run the simulation by one click. And what is done? Then first the mesh is generated. Afterwards, the calculation is done, and at the end, the simulation report is automatically generated. So at this point, I will open the part in which the meshing generation is already done, and at this phase, you can simply see your mesh, how it looks like, and if you are satisfied, you can go for the simulation. So basically, I can run the calculation, and you will see here the progress. Anytime during the simulation, you can generate the report. The light report contains the basic information, and the report is generated very quickly, or full report, which contains every important parameters which are evaluated during the computation. And at the end, so I can jump to the end of my simulation, so which is here. So if I click the TCFD manager, I can see that all the status bar are done, so the simulation is done, and the report is generated. So from the input geometry, I go over the meshing phase, which was automatically generated. Then I will get automatically, or not automatically, I can visualize the results directly here. And at the end of the simulation, I will get the report, which contains all necessary parameters evaluated after the simulation. So just quick overview. So some simulation statistics about the mesh, about the residuals. Here are the head of the pump for each simulated point. Here's of course the efficiency. So we can read the best efficiency point here. The torque, the axial force, which is the new feature in this version. So the axial force is automatically evaluated, and other stuff. Total pressure difference, total pressure per interfaces, which is a nice graph, so you can see the jumps of the total pressure through your turbomachinery design, velocity, magnitude, and many others. And at the end, there are some cavitation risk. So cavitation risk, how big volume, or in which, so how to say, the amount of the volume in which the cavitation can occur. And for example, the net positive suction head, which is a quantity representing a minimum head value required to keep the fluid from cavitation. So yeah, another useful parameter, and automatically generated blade-to-blade view. So with nice streamlines of the relative velocity, so we can see if there are some recirculation or not. And for example, the meridional average here, so the average over the wheel, and for example here we can see the static pressure. And of course you can make your own visualization directly within ParaView. So for example, you can visualize the pressure contours on the wheel or at the wheel, and you can provide a turbo unwrap filter. So you can make it a slice anywhere to visualize really the pressure contours at some relative coordinate between hub and shroud, or you can just visualize the blades at this unwrapped geometry. Okay, so I see that my time is up. So thank you for your attention, and I have to hand back the presentation to Luboš.
Okay, thank you, Radek, for your part of the presentation. It was nice to see. Okay, so perhaps I'll take back the presentation. Okay, so this is the example of turbo machinery CFD, and let's move in the webinar. Now it's time for your questions and our answers. So let's take a look what we have here. So I'm opening the panel with questions. I see we don't have many questions. Actually, I can see much better. This one is from Mario. Give me a second, please. Yes. Well. Yeah, it's like more business question from Mario Fede. Thank you for it. I will answer it personally. And yeah. Which brings me to the end of the list of questions. So I'm sorry, I can't see any more questions right now. So please put your questions. We still have a little bit of time, so we will gladly answer your questions. So yeah, I see one now. So it's from Hadi. So how can coupling between CFturbo and TCFD perhaps there should be be used for the optimization? Yes. Actually, the optimization is a very big topic all across the CFD field and all across, of course, the engineering field, and of course, turbo machinery field is full of thinking of optimization. So optimization is pretty complicated, and it's on the way. So I need to ask you to be a little bit more patient. Of course, CFturbo and TCFD go very well together. We are working on a smooth workflow, including optimization loop, which will basically switch between software, pieces of software, and it will create or find the best solution which is possible, but it's not available yet. So I would ask you for a little bit patience. Oliver, would you comment this?
Yes. All the things I have shown you are also possible to be scripted, which means you can run CFturbo together with all the exports, including the TCFD export, on a command line, which is necessary to bring that into an automatic optimization workflow. Right now, we have a students project running here in Dresden, which will contain a setup of such an automatic optimization workflow, and it looks very promising because the most important features are already there, and they are everything has to be capable of running in batch, and that's done for CFturbo as well as for TCFD. So it's just a question on when the student is going to finish the setup work.
Yeah, I agree. It's just behind the door. It's on the way. So let's do our best to make it happen. Okay, so I can see any more questions. So I guess we will conclude. And it's time anyway. So yeah, so I would like to thank everybody for coming, for paying your attention to this webinar. Yeah, of course, feel free to contact us in the future. I'm sure you know very well how to do that. The questions about CFturbo software are to be sent to CFturbo company, and the questions about TCFD are to be sent to CFD support. We will gladly support you in your projects. It's our job and also a pleasure. Well, so anything more to say, Oliver?
I just want to thank you for your time, and yeah, I hope we can come together somehow in the future. Thank you and bye bye.
Okay, Radek?
Yeah, just I want to thank you as well, and I want to say that we are really looking forward for future collaboration with you. And goodbye and have a nice day.
Okay, all right. So also thank you from me for your attention, and we are looking forward to collaborating with you. So stay tuned and bye bye for now.